Okay, so like I said, today we're going to be just expanding on graphs again. Hopefully, everybody got to look over the connected components and the randomness and this island matrix problem that I posted. And once again, I was saying that we're going to have to write a function that takes a 2D binary array and returns the number of islands. It says one islands because a one positive is going to represent an island. An island consists of ones that are connected to the north, south, east, or west. So a standalone one would be an island. In this case, like I'm saying, this would be an island, this would be an island, this would be an island, and this would be an island. These that are connected at an angle, like you would have northwest, northeast, we're only those are not connected. You're only connected if it's north, east, south, or west. Everybody understand what this is asking for. Um, if we were going to think of this in terms of translating the problem into the terminology that we've learned this week and just thought about the problem solving process with graphs. Remember, yesterday we said we need to translate it into that terminology that we've learned to build a graph and traverse the graph. I see somebody was typing. So does anybody think, what is it, if you think in terms of an island, what would you think in terms of a graph, in terms of the terminology that we're covering this week? What would an island be? It's not just a vertex because it can be more than one vertex, but what would overall that be? We just learned about it. It's two words. Yeah, well, they're connected components. Yeah, the connected vertices, connected components. Exactly. And adjacencies can be found. You know that we can find all of these adjacencies, these north, south, east, west that we're representing here with the two-dimensional graph with 2D array index arithmetic that we will look at a little bit more extensively later on when we're doing the code. One thing to point out, remember we talked about two different ways of representing a graph. There's an adjacency list and an adjacency matrix. This is not an adjacency matrix. That's a point that I want to make right now. Remember, an adjacency matrix makes all the possible combinations available. Let's say you had A, B, C, D, E, A, B, C, D, E, and this is indicating whether there was a connection between those elements like we were looking at the other day. This is a crude two-dimensional representation. Think of it like a game board or a matrix, a map. So you've got all these different points are like points on the map, and the ones represent land, an island. And if they're connected the way that they follow the rules, they stand for one island. So here's one island, here's an island, here's an island, here's an island. Anybody have any questions about that? The islands are just a connected component. The adjacencies can be found with a 2D array index arithmetic, and that this is not an adjacency matrix. So that's just a point we wanted to make so that you didn't get confused with that. Anybody have any idea, kind of want to put into words how you would think about going and trying to solve this problem? Doesn't have to be technical, just kind of, you can get on the mic too so you don't have to type. Anybody have an idea of how you might go about trying to solve this problem? Anybody? Well, we talked about how we were going to have to use how to find the adjacencies. And as we're looking for the adjacencies, what's something we're going to have to do over the graph?
I would try to iterate over each list or each array and get the index of where ones are located and compare it to the next array. And if the indexes for the ones match, then that means they're connected vertically. And then within a row, within an array, if the indexes for one are next to one another, then that means they're connected horizontally.
Yeah, so that's what we've got to look. We've got to look and see if they've got vertical and horizontal connections. We got to look, do they have a north? Do they have an east? Do they have a south? Do they have a west? And then once we get to another one, let's say we were traversing in this order and we were right here and we got to this neighbor. Well, then what do we have to do for each neighbor that we get to as well? We start out at a point, but then what do we have to do for each other point? Well, okay, we've got an island and we know the neighbor, a one. A one is going to be a neighbor. I guess I don't know if I didn't describe that, but the one will be the neighbor in the sense that it is part of the island. So the zeros are, the neighbors are the ones that are connected north, south, east, west in this representation that we've got. So yeah, you're going to want to find a way to be able to say what's to the left and the right, what's up and down, for lack of, a more technical term. You talked about iterating over it. Yeah, I think about traversing over the graph, or you were talking about iterating over each list. What are we going to have to keep track of? There's going to have to be a few things we have to keep track of while we're doing this. What things can you imagine that we'll have to track? Somebody. We're going to traverse over this graph, or over this matrix that we've got. We're going to have to find a way to find the adjacencies like we were talking about. What are we going to have to keep track of? Somebody. What's one of the first things we created yesterday with using a set that we were tracking?
Has it been visited?
Yeah, we need to keep track of where we visited. What else are we going to keep track of? Real simple here. We're trying to return something. So what else is going to probably want to keep a count on? We're returning how many islands there are. So maybe keep track of how many islands that we've encountered in total as we're incrementing. All right, let's do a little pseudocode. So I've got some code that's already here. I've got a stack implementation that I'll just go ahead and open up because we'll need it later. And then I've also got the islands that we will use here in a bit. We were going to pseudocode the island counter. It's going to take in the matrix simply being these islands that we're defining here, like we showed over here. And the first thing we're going to do is create a visited matrix. So it's going to be a little bit more complex than just creating a visited set, because we're actually going to have to create a matrix that's showing whether each of these points has been visited. And we're going to walk through each cell in the matrix. And what do we normally do with these as we're traversing through? What's the first thing that we always check for when we get to each spot? If in words, in pseudocode, what do we look for? We're traversing over a graph to follow a very specific rule over traversing and or searching in a graph. What do we need to check for? Yeah, see if it's been visited. It has not been visited. We can say when we reach a 1, which is the landmass. All right, so we're going to traverse over this and we're going to start looking for 1s. When we hit a 1, we know we've found an island, but we got to find all of the 1s that are connected to that 1 in this north, south, east, west way so that we don't count that island twice, if that makes sense. We got to get together everything and figure out what's this entire island. Remember, these islands are connected components. What comes to mind here that would be able, so these connected components, we're looking for neighbors. We've talked about what's a neighbor, a 1 that's north, south, east, west. And then we said for these neighbors, we're going to have to look for the neighbors of the neighbors. What does that make you think of? What? Looking for the neighbors of a neighbor. What does this make somebody think of? Yeah, breadth first traversal. It's a depth, but remember the neighbor got the traversal part. Remember the depth first looks for the neighbor, and the neighbor, the neighbor, the neighbor, the neighbor. A breadth first looks at one level, then it looks at the neighbors of that level, then it looks at the neighbors for the next level. Remember, so it's going through each level as it goes, whereas the depth first keeps going down. It's looking for the neighbor and then the neighbor and then the neighbor and the neighbor. So it's a depth first that we're thinking of here. But yeah, the spot on thinking in terms of the traversal, because I certainly didn't lead the question. But it's kind of a weird, you just have to know kind of, it's a little weird when you put it into words saying looking for the neighbor of the neighbor as opposed to looking for all the neighbors. But if you think about it, the breadth first search is going to look at all of the neighbors first. A depth first search is going to look at all of the neighbors of the neighbors and the neighbors of the neighbors, the neighbors and the neighbors, the neighbors, the neighbors, and so forth first. So what this will allow us to do, what I'm saying is when we reach a 1, we will do a DFT and mark as visited, as we always do. And increment the counter by 1 when we're done. I'm going to put up a poll because I want questions right now, because if there's no questions, I'm going to be shocked. Does everyone understand what we're trying to do? Because if not, I'm going to try to take a little bit more time to answer. I don't just mean, yeah, go ahead.
Can you just like show from that example that we have of the islands how you're getting 4 islands from that?
Yeah.
Thank you.
Okay, so if you look right here, it's a little bit skewed, but if you think about this, like here, Here's your first island. We have a 1, so that's an island. And then anything that's connected to it, north, south, east, or west, so we have a component south of it. And then this component has something to the west of it. And now there's no other relationship. So there's one island right there. And then here, you have the same thing. You have one south and one east. Then you have another one, and you have one that's to the south. And then you have this where one's to the south and one's to the east. Remember, these relationships don't count. We're not looking at southeast, southwest. We're only looking at north, south, east, west. Does that make sense?
Yeah, that makes sense.
So it's just looking at the neighbors, but the neighbors are defined as those that also are a 1. It's a little bit of an abstraction, the whole problem, but that's what we're looking for. So
I was only seeing 3 from this one. 1, 2, 3.
So you should see the heck. Let me draw. One, 2, 3, 4. Make sense now?
Okay, so it's not, it can be north and south, will also make an island. It doesn't have to have east or west all the time.
It does not have to have anything. A 1 by itself, that's an important point to make. A 1 by itself is an island, but the island as a whole consists of any component that is north, south, east, or west of the original start point, and then we continue to do that. So any component, so right here, let's say, if this had been a 1, this would be one whole island because everything's connected north, south, east, or west. But because this is the only connection and we're not counting a northeast, this would be at an angle. And what this allows us to do is this allows us to do some real easy adjacency or 2D array math to be able to get the points. Does that make sense?
Yes, thank you.
Cool. I see a couple questions here, so we will jump to that. Can BFS be used to solve this problem instead of DFS? I'm not going to say it couldn't. There may be some stretch of a way to do it. But if you think about it, we're trying to find in one pass, we've got to find in one pass what all is connected to this. And we're going to have a custom function to define those neighbors. But think about if we're looking for the neighbors of the neighbor and then the neighbors of the neighbor of the neighbor and all that, that is following what a depth first search does. A breadth first search, like I said, that would be a question to ask Brady. It may be possible to use it, but a depth first search is definitely by far most intuitive and most suitable to solve it. That's the best answer I can give on that one. Any other questions? Any more questions? So we're going to go here into this pseudocode. We're going to create a visited matrix, and we're just going to make that an empty list. And we're going to walk through each cell in the matrix so we can say for I in range, say the length of the matrix. Actually, this is still going to be part of making the matrix. I put this in the wrong spot. So we'll say for I in range length of the matrix, we'll say visited dot append false times length of the matrix at 0. So what we're doing here is we're saying for I in range length of the matrix, the length of the matrix is simply going to be how many elements the outer, remember this is a two-dimensional matrix, so in this case, you are dealing with 1, 2, 3, 4, 5. So it's looking for this. So it's going to iterate over 5 times for each array that we've got, and we're just saying visited.append. We're appending a false, an array of falses, times the length of the matrix at 0. So now we're asking how long this is. The length of the matrix at 0 is going to look at the length of this list, and this is also 5. So it's going to just create this. This statement right here, this Python creates this. We're simply going to iterate over 1, 2, 3, 4 times and fill this full of falses so that we have a representation of this entire island full of falses that it has not been visited. If that's not clear why we're doing that, you can speak up and ask any questions.
Would you turn them into true when you find a 1?
Yes, we will. We will definitely mark that as visited, and that's why we're doing it the way we did it. You could also do these with 0 1s. The reason we're doing these the way that we are doing them is because we're using the matrix that's representing the island with 0 1s. This is just a little bit of a way in my mind to keep these separate because they're two separate things. And the confusion of this problem sometimes arises in the fact that we've got two different two-dimensional arrays going on. One's keeping track of visited, one's our actual game board or map, whatever you want to think of it that we're using. So we've just created, this has just created this full of falses is what this has done in Python. And we will initiate actually an island count as well, equal to 0. We're going to walk through each cell in the matrix. So to do that, remember we've got a two-dimensional matrix. So to walk through it, we're going to have to actually have what? How are we going to walk through each cell in this matrix? Something with the loops. It's a type of loop or a terminology used with loops. Nested loop. So we're going to say for X in range length of matrix at 0, which is the length of that first element in the matrix in that two-dimensional array. And then we can say for Y in range length of the matrix and we're going to look if it's not been visited. So to check if it's been visited, we can just say if not, and we'll call the visited array. And we will check points Y and X in that array. So we're simply saying if this does not exist, it's going to, remember this is looking for a Boolean, and this is a false at this point. So it's saying what is visited at X and Y, and they're all false. So saying if it's not been visited, when we reach a 1, when we reach our definition of an island. So we can say now if matrix, remember we're looking at the matrix at that same coordinate y and x equals to 1. Remember we're looking for the ones. And then says do a depth first traversal and mark each as visited. So we will define this later, but we're going to do a DFT and we're going to give it the X and the Y coordinate that we're at. We're going to need to give it the matrix, and also we need to give it the visited. We're going to be passing that visited back and forth. Once this DFT is done, this will have marked everything connected on these islands is visited, so we won't go back over them, and then we just increment the island counter by 1. And then at the very end, outside of the loop, we will simply return the island count. Okay, something I want to point out here, and you can put it, does anyone have any questions over what we did? Something I want to point out that's not necessarily intuitive is right here, we're dealing with X and Y coordinates, and when we're dealing with this two-dimensional array, this is our X, and think of this as a Y. It's not your regular Cartesian system that we're dealing with. But this is X going 0, 1, 2, 3, 4. This is Y going 0, 1, 2, 3, if that makes sense. We're dealing with all these in terms of an X and a Y, but the reason we check for YX, we're iterating from X, and then the nested loop is for Y, but we're checking YX because Y, when this loop first iterates, it's always going to be 0, and then Y is going to iterate from 0 to whatever range we have here. So with this always being 0, you're always going to be at this first point and you're moving down. So how we're traversing this, so I was kind of showing you earlier, is we're checking here, and then we're checking here, 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 and then we're checking. This is how we're traversing over this graph. So that's the reason we're giving it YX and these are reversed. Does anybody have any questions on that? I don't want to spend a whole lot of time talking about it. It's something that if you go back and you look at it long enough, eventually it makes sense if it doesn't make sense at first. But know that this is representing the X coordinates, this is representing the Y, this is increasing, and we're traversing it top to bottom, top to bottom, top to bottom, if you would. And whenever we find a 1, so just to kind of go back over this again, we created a visited, just like we did the set yesterday. We populated that like we talked about with falses. We set our island count to 0. We're going to traverse all the X's and all the Y's to be able to cover all of these points in this two-dimensional array. And if we're just going to say if it has not been visited, when we reach a 1, visited is stored up here. The 1 is in the matrix here, the island that will feed this right here. We're simply going to say visited, and we're going to mark everything connected by neighbors with this depth first traversal that we'll define later, giving it the X, the Y, the matrix, and the visited. Any questions over that? I'll see. Yeah, the way that we're traversing, the way that we're going about traversing this graph, you're checking this point, then this point, then this point, then this point, then this point. So here we don't have a 0. Then we reach a 1. So we're going to perform a DFT, and we'll be able to mark these all as visited. And we're going to keep going. Oh, here's a 1. We're going to have a DFT and mark these all as visited. Then we'll start searching through here. These have already all been visited. They were visited in this DFT. Keep going here. This was also visited with the DFT that started here. And we'll do here. Oh, here's a new one. So the DFT will discover this, and then this will be skipped because it's already visited. And then we'll trigger the same here. And then this will keep going. And we'll traverse here, but this will have already been visited. Does this make sense? This is the heart of the entire problem-solving process here that I'm trying to take some time laying out. I'm not going to spend as much time talking about some of this other stuff, but does that make sense to everyone? If it doesn't, okay. Yeah, it takes a while to kind of walk through the code, define the problem, walk through the code, and walk through how the code is working and see the code in place and look down. That's why I put these down here in all of this down here so that I would be able to reference back to it. Cool. So I already have my stack that I brought in because remember, for a DFT, we're going to use a stack. And so if we wanted to make the DFT, we can say, we'll just call it DFT, and we're going to have the same parameters that we are feeding it, the X and the Y, the matrix, and the visited. So we're going to make an empty stack. To say this is basically talking back through what we did the other day with a DFT, a depth first traversal. We're simply going to have a few little changes to it because of the way we're going to deal with this. So we're going to make a stack. What do we do after we make a stack? We do something with a vertex. What do we do with a stack in a DFT after we create the stack? We're doing a depth first traversal. Yeah, we're going to push it. So we can say, push it real good. And we're going to push XY. Can somebody tell me right here what this is? Why we have double parens here? Why? What is this? Yeah, well, it's the cell, it's the coordinate, but specifically programmatic. Yeah, Brian, it's a tuple. So remember that tuples cannot be changed once they're created. You cannot remove something, you cannot change a value, you cannot add a value. And in this case, this tuple that we're creating is going to just be like an XY coordinate pair. So this is a real convenient way for us to be able to store these coordinates in a tuple. And like I said, just remember that they are accessible by index, they are ordered, and they are accessible. They're ordered, but they are immutable. Ordered, but immutable. They don't have to be 2. They can be 3, 4, 5, 6, or 1,000 in length, but this is a real convenient way to do that. And then while the stack's not empty, like we always do, say while stack.size is greater than 0. What do we do with the stack in a DFT when the stack size is greater than 0? We still got things to search. So by nature of how we go, the in and the out and everything of a stack, what do we do? I need to pull. Starts with a P. Pop, that's what I was looking for. We're going to pop the stack. So when we pop the stack, we're going to get this tuple. So we can say X equals, remember we've set V to be this popped vertex, V at 0, because we can access a tuple by index because they're ordered, V at 1. And then we will say, check if it's been visited. And remember, once again, we're having to give these coordinates backwards the way we're traversing it. And this is just looking, is this in the visited, is it a true or a false? It's evaluating a Boolean. We're going to mark it as visited. Someone asked about this earlier. So we will say visited at Y x equals true. You can make these zeros ones. This was just a way to me to make this a little bit more easy to follow which matrix we're dealing with. So we're just going to change it to true. And then what would we do after that? What do we do in a DFT? It's not been visited. Now it's been visited. What do we have to do for it? We talked about that in terms of the ones on the island. What do we need to deal with now? Yeah, we need to find the neighbors. So we will say for neighbor, I'm going to iterate over all the neighbor. For neighbor in get neighbors, which we will define next. And we'll have to, for getting neighbors, we'll have to give it the x and the y tuple and the matrix. And we'll just push that onto the stack. This is just the same as pushing with the vertex is simply the tuple this time. We're going to put that vertex on the stack. Then at the very end, we will return visited. So we're doing a depth first traversal. We're taking in the x and the y coordinate, the matrix, the map, and our visited. I'm doing this DFT every time we come to a 1 so that we can figure out how far this island spans. So we're going to make a stack. We push that starting point onto the stack, the starting point here being the x and the y that we create a tuple with. While the stack is greater than 0, we just pop off of it as usual. And we're going to make an x and a y based on accessing the element indexes of the tuple, the indices, and then the typical if not visited. And we'll give it that y and x. Remember, these are in a reverse order because of what we discussed up top. Visited yx equals true, and then for the neighbor and all that, we're going to get all the neighbors and push them onto the stack. And that while loop's going to keep running until we run out of neighbors being able to find. Remember, the neighbors are the ones. So we're going to have to define a function to find all the ones that follow the rules that we were given. And that really is the last thing we're going to have to do. So finally here, to get the neighbors, this is going to be where we talked about doing the adjacency math, or doing the math to find the adjacencies. We're going to take in a vertex, that tuple, and we're taking in that matrix. We'll call it graph matrix, so that we're clear on what we're taking in, since we're only taking in one, not the matrix and the visited. We'll do the same and say x equals the vertex at 0, y equals the vertex at 1. And we're going to need to make an array of neighbors. So we'll go ahead and define that. So our goal here is to return the neighbors, but we're going to have to find those neighbors. So anybody want to talk about what they would do to try to find these neighbors? Just with these numbers that we get, it's going to be easy. It's just using some math. Let's just say, let me, if we wanted to do, let's think of it like this. We'll say check north, check south. We'll say check east. Check west. Anybody have any ideas on how they would want to go about doing that? Getting close to the first hour here. We're going to finish this, run this, take any questions, and then take a break, and we'll move on to the second part. But just bear with me for a little bit here. So I'm thinking here, if we said if y is greater than 0 and graph matrix at y minus 1 and at x, remember we're feeding this in yx order because of what we discussed earlier, equals to 1, then we could say neighbors dot append. And remember, we're putting these, and we could say x and y minus 1 as we did. We're putting these into a list and appending because later on we're going to iterate over through and push each of those. So we want something that's iterable, so we're going to put those neighbors. So here we're saying if y is greater than 0 that we've gotten. So if we're at, I keep changing this and moving it back. So if we're at this point right here, y is 0. So we want y to be greater than 0. Why? Why do we want y to be greater than 0 if we're going to check north? Remember, x and y. Why does y need to be greater than 0 to check north? Yeah, there's got to be something above it. There's no north right here, so we don't need to check for here. So here we can check, here we can check, here we can check, here we can check. So just if y greater than 0, and then y minus 1, so just we're looking at the point above it. Y minus 1 and the same x equals to 1, then we'll know that's a neighbor, and we'll append that coordinate. And so likewise, if we were going to check south, what would we do? Yeah. So we can say, for this one, we'll have to say if y is less than the length of the graph matrix minus 1 and graph and the plus that you talked about, the graph matrix of y plus 1 and x equals to 1, then the same neighbors dot append x y plus 1. We're going to say here, long as the y is less than the length. Now remember, this works, but we need to say minus 1 because y is going to be 0, 1, 2, 3, 4. The length is 5, so we want 0, 1, 2, 3, 4. Same thing we always did in JavaScript with the minus 1. And it needs to be less than that. For the same reason, if we're checking south, we're only going to be able to check south here, 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 and here. When we're at this point, this does not meet this condition. And then we're simply checking and we're changing the y coordinate to plus 1 to look south. It's going down 1 in the same x coordinate. And so for east, we're going to have to look at x and say if x is less than the length of the graph matrix at 0, and just going to do 0 minus 1, and graph matrix at y and x plus 1 equals to 1. Neighbors dot append the same, and we will append x plus 1 and y. X is less than the length of graph matrix at 0 minus 1 and graph matrix y at x plus 1 equals to 1. And then to check west, obviously it's going to be the same thinking that we did up above. If x is greater than 0 and graph matrix at y and x minus 1 equals to 1, and we'll append that. X minus 1 and y. And then we return the neighbors. So for each point, we're just sending it down and we're checking those 4 places, just using math on the, if we send it here, we're going to check north, south, east, west, just using that simple matrix math. Anybody have any questions? So if we try to run this, this is going to call island counter. It's just going to return the island count, but that's not actually going to show in the terminal. So maybe if we put print island count, that might help. And indeed, we actually didn't have any errors, and we got 4 for the first one, and 13 is the correct answer for the second one. I am going to take any questions here on what we did, any questions on the methodology that we used for problem solving, any Python syntax questions, any graph traversal questions, any questions to the logic of why we went about solving this the way we did, about why the code is functioning the way it did. So I'll say any questions. You can get on the mic. You can type here. You can type in the channel. If nobody has any questions, we'll go to a quick break. And certainly there's got to be some questions in here. Any questions? We got 14 people in the channels, so speaking of, if you have a question, type it here, type it in the channel, speak, and I will do my best to answer anything you got. How do you determine the north, south, west, and east? So I'm afraid I don't understand the question. So you're just meaning, like, mathematically, how do we determine what's north, south, west, and east?
Yeah, I don't understand why like when you do note, it's like y negative one, y minus one thing. I don't understand that part of this.
Okay, so when we're looking for the neighbors, think back. So say we've given, you'd agree that this point right here is x equal to 1 and y equal to 1, correct? We got
Mhm.
0, y 1. This is x, so this is 1, 1, correct?
Yeah.
Okay. So we've got 1, 1. So we go through each of these. We're here, we're going to check north. So we're going to say is y greater than 0? Yes. And we're going to look at the graph matrix of y minus 1 at x. So this is 1, 1. We're looking at 0, 1. That allows us to look north. It's just, it makes sense if you lay this, the classic way of writing out this matrix with the commas and then the new line and all that. North is just simply above it, east is to the right, south is below it, west is to the left. But in accessing those, we're just using the math. If we want to go up, we just subtract 1 off the y in this case, because the way we've got the y setting up running top to bottom. So we check, we're here, this checks this coordinate here, y is 0, x is 1, that's this coordinate. If this equals to 1, then this is a neighbor, and we append that same coordinate that we checked into the neighbors. And then the same thing for the graph, but to check south, let's say, is y less than the length of graph matrix minus 1? That's going to be, if it's asking is y less than the length of graph matrix, that's 5, minus 1 is 4. Is y less than 4? It's 1, it's true. Is graph matrix y plus 1 at x equal to 1? Y plus 1 here, this would be the y of 2 and x of 1, so we're looking here. No, we got a 0, so we're not going to do this. And same for the east and the west. That make more sense? The east is just going to look here. West is going to look here. You're just manipulating the numbers here in this coordinate system to be able to look up, down, left, and right in the matrix.
Okay. Now the question, why do we pass in the neighbor as tuplet?
Why do you pass in the neighbor as what?
The tuplet? No,
The tuple?
yeah, tuple.
A tuple, you don't have to, you could pass it in as the, are you meaning for the get neighbors? Why are you passing it in as a tuple right here instead of just XY?
I mean the neighbor dot append.
Well, because remember, each neighbor that we made up here, a neighbor needs to be a single element. And each time up here, we're in the DFT, we're popping that tuple, that one element, and then accessing the x and y off that element. You'd have to, if you stored it in more than one element, you'd have to pop it twice or something weird like that. So the tuple allows you to use one element and store the x and the y value, the coordinate values.
Okay.
Does that make sense?
Yeah, definitely.
Yeah, so we're appending them as a tuple because those neighbors are going to get pushed onto the stack. And remember, as we pop the stack, we pop it an element at a time. So we need to pop one element. And the easy thing, you could use anything that you wanted there. You could use a dictionary. You could use an array. But a tuple just mathematically makes more sense and is easy to deal with.
Okay.
Tuples are commonly used to represent coordinates because of the fact that they are immutable and because of the fact that they are ordered so you can access each of them. And it's just a common thing in any language to represent coordinates as tuples. And this basically is coordinates. It's a different XY system that we're dealing with here. We're not thinking the typical cross with the positive X and the negative X and the positive Y, the 4 planes and the Cartesian coordinate system. We've just got positive X's and positive Y's. And we're running the positive Y's from top to bottom.
Got it.
Anybody else have any questions on how we did that? I'm going to drop all this code in the channel, and actually I'll just drop it at the end because I'm going to have some more and I'm just going to add it to this. But it's 10 after the hour. Be back at 15 after the hour, so 5-minute break, and we will see you after that to cover kind of what you're going into with your social graph. You could rename it to whatever you wanted. Yeah, absolutely. And that may be a little bit more explicit since we're having to. I just like using X and Y's because I come from a math background, so I always think in terms of X and Y. But yeah, you could definitely rename those. These are basically placeholders. We can name them what we want. But yeah, I know it does get a little bit confusing with the fact that we're feeding the coordinates in as XYs, we're accessing them as XYs, but then we're having to put them into reverse order to be able to represent this X moving left to right increasing and the Y moving top to bottom increasing. But yeah, it's a good thought. All right, give everybody just a second to get back in. This is just part of your repo for day 3. I put the link in. Everybody should be back now. Can you hear me okay? Just checking. Somebody type in the channel if they can hear me okay. Cool. Cool, cool, cool. All right. And I'm going to give everybody, I dropped the link up here, so I'll give everybody a second to read over this social graph problem. Give them about a minute or two for everybody to read that over. About one more minute to read over this first. This first piece. So we know that all social networks are graphs. What would the extended social network? So they talk about you're going to build a social network and friends, and there's friends of friends, and then there's friends of friends of friends, and an extended social network. What is an extended social network? What are those friends and friends of friends and friends of friends and friends? What we were talking about this terminology over. What are they also? It's 2 words. Yeah, they're connected components. The social network, like we talked about the first day, is just a graph, is all it is. And the extended social network, these friends of friends and friends, that's, you could say, that's connected components. And we can find those components doing a traversal. I don't remember who asked earlier if you could use a BFT instead of a depth first traversal, but the more I thought about it, you should be able to use the BFT to find it. It's just not, like I said, to me at least, it's not the most intuitive and it's not the most suitable for the situation. But you definitely could make a method, because with something like here, you could use a BFT or a depth first. And something else you've got to remember, you can find them whatever way you want. The 2 ways that you're going to traverse a graph are breadth first and depth first. And a point that we saw earlier, that you can start doing this traversal from anywhere in the graph. You know, you're not always going to be moving from the top to the bottom like we represented in the classic binary tree structure or something like that, you know, but it's looking at all of the neighbors first versus looking at the neighbor and then the neighbor of the neighbor and then the neighbors of the neighbors. So since we're looking for the neighbors and the neighbors of the neighbors in this case, it just is more intuitive to use the depth first traversal. And so once again, we're going to translate the problem into graph terminology, which we've been thinking about already. We've got the connected components. We know these connected components can be found using a BFT or a DFT. Also up here, let me go look where it was. I know I saw it somewhere. Yeah, here they're wanting to be able to see how it will scale. So they're asking you to create a feature that creates a large number of users to the network and assigns them a random distribution of friends. So to do that, we'll have to actually have an input of like an average friends per user as well. And that would just be like a total friendships over number of users. But that's not really graph terminology, and we'll cover that as we code. So for today, we're going to continue on with this problem tomorrow, and you will be working today with the social graph, as you're seeing here in the repo. The degrees of separation simply are speaking of how many, a friend of a friend, there's 1 degree, as friend of a friend of a friend, obviously as that increases, the degrees of separation increase, so that should be fairly intuitive. What does this look like right here that we've got, that I've got highlighted? What's that look like? So representation of a graph, what kind of representation of a graph is that? See, somebody was typing. Directed? I was thinking in terms of what type of a representation of a graph that was, in the terms of, we talked about, yeah, an adjacency list. That's what I was looking for. Yeah, whether it's directed or undirected would depend on how these coordinates related. Is there a relationship going both ways? In this case, with a social network, there is a relationship going. It's bidirectional or undirected, because when you're friends with somebody, they have to be friends with you as well. But yeah, it's an adjacency list. So we have 0.1 and it's connected to 8, 10, 5. And then if you look at 0.8, it's connected to 0.1 and 5. So 1's connected to 8, 8's connected to 1. So that's bidirectional, undirected. And it's an adjacency list, like we said we would be doing with. So the code we're going to work on today, I'm going to do some pseudocode, and we're going to code part of it out, and then you'll just take this to move forward with your problem today. First thing we got to do is populate the graph. And that can be a little tricky in itself. So if we were going to pseudocode this out, this will take in self. And to populate the graph, we need to know how many total users we have in the social network and the average friendships. Because remember, we're going to have to be able to populate this randomly to run tests. So we need to know how many users and how if we ask how many average friendships, what is something in the terminology of graphs that we talked about the other day? We spoke specifically about social graphs, a term, an attribute of a graph that includes terminology. What would the average number of friendships represent? It's a term we use in physics. Average number of friendships. It's going to be comparing the friendships that we have to the total number of users that we have. Average friendships is giving friends per user. And when we talked about a graph being dense versus sparse, as those average friendships go up, what happens? Yeah, it becomes more dense. As it becomes more dense, what problem do we run into? We talked about how an adjacent, theoretically an adjacency matrix would represent a very dense graph with, I don't remember if it was time complexity or space complexity. Somebody remember? Remember, with these graphs, a lot of the methods, no matter what we use, whether it's an adjacency matrix or an adjacency list, the access times are the same, even though an adjacency list does give us some advantages in terms of access time. But what complexity can become a problem? Time complexity we talked about. What about the space complexity? Space complexity, as we become more dense, can become the issue that we can address with the graph. And we'll see more of that. You'll see more of that as you work through the problem today. And we will work through that tomorrow as well for our final GP. So if we're going to populate the graph, the first thing we would want to do is reset the graph. And that would just be in case we had already actually created a graph and we were going to run it again, we need to be able to reset it. So we'll say self.lastID equals 0. This is simply a counter. We're going to use a numerical counter here. So the last ID will simply be 0 at this point. Users, this can be your names or however you're going to do it, your IDs. And the friendships. Remember, these friendships are going to be showing the relationships between these users. Then we'll want to add users. Somehow we're going to have to create friendships. After we create the friendships, we'll have to generate all the possible friendship combinations. When we're making the friend, so we basically, to randomly populate the graph, the way we're going to go about doing it, we have all our users, so we need to generate all possible friendship combinations that there are. Everybody being friends with everybody. Can you think of a problem as we're probably going to have to iterate through or do something like that in creating these friendships that could cause both time and space complexity problem? There's something that we don't want to create. While we're creating these friendships, we're going to generate all the possible friendships, but what would be something that would be easy to do while we were generating all these possible friendships? So we're going to look at John, and we're going to look at everybody else in the group, and we're going to create a friendship between John and them, or a possible friendship. So what could be a problem then when you move on to the next person of the group that you're trying to avoid here to be more efficient? See, Brian is typing. Nested for loops. Yeah, I mean, you would want to watch out for that, and in some cases we just end up nesting for loops. What I was thinking is that, let's see what Tico says. But yeah, we always want to look out for nested for loops because those do cause a problem with the time complexity, and they definitely can cause a problem with the space complexity depending on whether we're having to add more memory. And in this case, we are creating duplicates of edges, friendships, exactly, Tico. So we need to avoid the duplicates. We'll say by ensuring the first number is smaller than the second. We'll see more of that here in a second. Once we've created all these, we're going to shuffle them as well. We're going to create friendships for the first X pairs of the list. We can say X is determined by the formula num users times the average ships divided by 2. Why are we dividing by 2 here? We need to grab X amount of pairs after we've created all these friendship combinations, avoided duplicates, we shuffled the possible friendships, so we don't just get the first X amount that we generated, we've shuffled them. We're going to create friendships for the first X pairs of the list, and X is determined by taking the number of users times the average friendship. So if there's 10 users and 10 average friendships, that's going to be a total of 100. But why would we divide by 2? We kind of already touched on this. Just why do we divide by 2 to know how many pairs to grab for the friendships? Number of users times average friendships. Yep, so we don't want duplicates, and at the same time, when we're saying num users times average friendships, we're dividing by 2 because the friendship work goes both ways. So we just simply use this floor division here because we can't have a decimal. We have to have an integer for friendships, so we always use this floor division. So we're going to add users. We could say for I in range 0 num users, we'll use template literal here. You don't have the add user, you will code that out yourself, but that's what that add user is that you're simply going to be adding a user to your empty users here from 0 to the number of users. Remember, when you do the range, this is actually not inclusive, so that's why we go from 0 to number of users. So if we have 100 users, this is going to go from 0 to 99, which is 100 different indexes. And we'll just say self.addUser, and we're using this template literal format here, and we're just naming it user I. So you're going to have user 0, user 1, user 2, user 3. So we're going to generate all the possible friendship combinations. We'll just store this in an array again. We'll say possible friendships equals that. And remember, we want to avoid duplicates by ensuring the first number is smaller than the second. So what that means, as we're iterating through on line 92, we're going to make no duplicates by simply creating possible friendships for everything in front of it that hasn't already been iterated over. So if we're at 50 of 100, we're only going to pair 50 up with 51, 52, 53, 54. We don't need to worry about 0 through 49 because we've already paired them with everything in front of it, so we've already covered 50. That doesn't make sense, somebody type. So while we're avoiding the duplicates here on line 98, we can say for user ID and self.users, we're using user ID plus 1 and self.last ID plus 1. So we've got the self.users here. Should fix that problem. We're going through all the users, and then we're creating the second friend ID in a range of user ID plus 1. Why do we say user ID plus 1? Why don't we start at user ID? Remember, the lower end of a range is inclusive, so why do we say user ID plus 1? Why do we say user ID plus 1? Yeah, you can't be friends with yourself. So we're gonna remember we're only gonna look what's beyond it. So for the very first user, we're gonna make those possible friendships with everybody. But then the second user, we don't need to worry about the first user that we just went over because we've already created that friendship. And when we create a friendship, we create a two-way relationship. Or can you? Looks like I forgot a semicolon there. And then we take self last ID. Remember, the last ID starts at 0 so for each user that we add, we'll just iterate up the last ID is going to be that last user. Why do we say self.last ID plus 1? Why do we use that for the range? Why don't we just say self.last ID? Remember, we're iterating over remember that in Python here that the range, this number is inclusive, this number is not inclusive. So if we need to include this last number, we actually need to say plus 1 to include that last ID, or it's going to exclude that last ID. And then we've talked about the random before. We'll just shuffle these possible friendships. It's flagging that random because I didn't import it up at the top. And finally, for this last bit of pseudocode, we can say for I in range, num users times average, friendships divided by 2, friendships equals possible friendships at the I. And we will just add that friendship. So for I in range, the number of users times the average friendships divided by 2. This before we talked about why we need to divide it by 2. So we've created all the possible friendships here. Created every possible friendship that there was. We avoided duplicates, like we talked about. Then we shuffled them. We just got this little warning right here because we didn't import shuffle. and then we're just going to iterate over all of these. Say friendships equals possible friendships at the I, whatever we're at the I, and we're going to add the friendship. I think actually that's why. And remember, the way that we're representing the friendship is the 0 and the 1 index are the user ID and the friend ID, and we're simply saying add the friendship at the 0. We're just adding, and remember the add friendship will need a user ID and a friend ID. So we're just picking the user ID and the friend ID here. It's kind of to go back over it. You're populating your graph. You're going to take in the number of users and the average friendships. You reset everything involving the graph, the users, the friendships, and the last ID. You add the users based on the number of users, and we're just naming it user 0, user 1, user 2. Creating possible friendships, we're going to iterate over all the user IDs, and then we're going to say if the user ID is in the range 1 above it, because you can't be friends with yourself all the way to the end, so we're not going to pay attention to anything that was behind it. We're going to append that possible friendship, the user ID and the friend ID. Remember, that's just what we've created up here. We're going to shuffle that so we have randomness. You just need to import your random. Then we're going to iterate over that number of users times average friendships floor division by 2 times, because of the reason we talked about that two-way nature of friendships. And then we're just simply accessing the friendships by going to that element that we're at. So we've made all our possible friendships, we shuffled them, then we're just going to start grabbing each friendship as we go along. And with that possible friendship, we're actually going to add a real friendship to the graph using that user ID and the friend ID. Anybody have any questions? Anybody have any questions? I'm going to put all this code in the channel. Anybody have any questions with anything that we just did? Yeah, like I said, this week is definitely dense. That's why I wanted to take the time to try to explain some of the nuances of this in detail. You can go back over the video. You can look through the code. I tried to comment out some of the code as we went. Tried to continue to use the problem-solving method, use the graph terminology, use the terminology of the different ways that we use these graphs, that we traverse these graphs. Tried to cover all the Python syntax, but yeah, if it's not, just know that, you know, you've got today, and we're going to be working more on this tomorrow with this same code, with this social graph, and this all plays into what you're going to be doing with the sprint. So today you've got your assignment, and then tomorrow we'll have one last GP that will go over some last loose ends, and we'll talk about the sprint itself. But if nobody has any questions, I'm going to go ahead and end this. We got about 15 minutes before the hour. I'll get the video posted. I'll do that right away since people are wanting to rewatch it. Takes a minute to process. Come here tomorrow at 8 o'clock, ready for whiteboarding if you're doing whiteboarding. If you're not doing whiteboarding, you've got that hour. And then we'll have the GP, and at 11 o'clock, you'll receive your sprint, and it'll be due regular sprint time on Fridays. All right, I'll go ahead and get this posted. Thank you, everyone. And y'all have a good afternoon. Don't forget to use the 20-minute rule, use the help channel, use your PMs, DM me. I'm not sure if there's going to be a Q&A today because they're only officially Tuesday, Thursday, but there may be, so watch the channel. Thank you, everyone.